Is Rubio, and this is my lab 4, Oscillations for Physics 2211. Introduction. So for the purpose of this lab, we were aiming to make predictions of oscillating motion with data using tracker and glowscript, and then we were to see if the model created is consistent with the energy principles. And for our result, we found out that it is actually, because the total energy throughout the closed system is consistently at 0, meaning that all the energies at play cancel each other out. Physics principles that we will be using. First, we got Newton's second law of motion, being that F net is equal to the change in momentum over the change in time. And then we are able to derive this to get the position update formula and the velocity update formula, and other formulas as well, such as the kinetic energy formula that we use later on. And second, we have the energy principle, being that a system's change in energy is equal to the work done by surroundings and thermal energy together, which, as I said previously, we find out is true in this case with the results of our model. A picture of our experiment in tracker. We see the 100 tracked points already there, and on the right we see the basically just a plot of the x position and the y position as time goes on, and we see that the waves are there, as is consistent with oscillation. Details of our experiment. The system consists of a mass being swung from the spring, as we saw on the previous slide, and the surroundings being the external forces of gravity and the spring force. And we actually made sure to let go of the spring rather than push it, so that it doesn't have a initial velocity. And now for our initial conditions and assumptions. Our object is not pushed by the person conducting the experiment, but rather let go, as to not add another external force, as I mentioned just now. And for our initial conditions, the mass is 0.402 kilograms, the relaxed length is 0.123 meters, the initial position is negative 0.12 on the x component and negative 0.65 in the y component, no initial velocity as I mentioned earlier, and the spring constant is 6.8. The initial conditions that I talked about in the previous slide, this is the implementation in the code. So we see the first three lines are the mass of the object, and then the position and the velocity to begin with. And then we see gravity at play there, then our spring constant and the relaxed length of the spring. And for the next three lines, we see that we see L being just the vector of the spring, and we see L hat just being essentially L hat, the spring over the magnitude of the spring, or the orientation, and then S being the length of the spring, just magnitude over the beginning. And now for the next four lines, we're just essentially computing the energies based off of the formulas that we talked about earlier in the class. And then for the last line, we see total energy is equal to all three energies combined, so kinetic plus gravitational potential and then plus spring potential. Part of our code, arguably the most important part, we see the motion prediction loop. So we first define our initial energies, as we said earlier in the code, and then we have essentially just formulas for the three forces that are acting on the spring, or the two, and then F net being a combination of those two. And then we apply the momentum principle to update the velocity and position. And then we update the spring as we did earlier on in the code, with L, the orientation being L hat, and then the length being S, and then the axis and the trail. And then at the bottom, we again update the energies, and then at the end, total energy is just equal to all of them together. Now for the data versus model predictions. So as you can see here, the two graphs are pretty close together, and you can see an example of the output of our code with the spring there. The blue part is the model and the red part is the data, and as you can see, they're pretty close together. And for a possible error that could have occurred, it could be worked by external forces, since our data was acting in an open system. And then for another possible error, I could have just made a mistake when tracking the position of the data. Potential questions: is the energy principle satisfied? So as you can see here, we have three energies at play: kinetic, gravity, and spring. And then you can see the fourth line, delta E, is always at 0, so that means that all the energies always cancel out, which means that our energy principle is satisfied in our model. Another potential question: what does the estimate of oscillation periods mean? So for the x position, I've calculated an oscillation period being 6.0 1, 2. And then for the y position, I've calculated it to be 6.35. So as you can see, there's a little bit of a deviation there, which means that choosing different directions produces a deviation in the period. And, that's just going to change the results a little bit. Thank you for your time. I hope you have a good day. Don't forget to like, subscribe, and please don't leave a comment.